the technical difficulties. My laptop's a bit temperamental sometimes. I'll just give a quick introduction of who I am. I'm Adam Bond. I'm a fourth-year PhD student at the University of Dundee under the supervision of Professor Alessio Ciulli. And we're just about to move into our new centre for targeted protein degradation, and that's one of our main focuses of and the fields that we show expertise in our group. The next few slides, I'm just going to show basically a case study of a paper we recently published at the end of last year. And I'll give a brief introduction to what PROTACs are for those of you who haven't come across them before, and how they are this new, well, recent modality to basically overtake just normal inhibition. So first of all, what is a PROTAC? So PROTAC stand for proteolysis targeting chimeras, and these are heterobifunctional molecules which exploit and hijack the ubiquitin proteasome system. As you can see from the right, they're comprised of two ligands. One ligand binds to an E3 ligase, and the other binds to their target protein of choice. And this is these two are connected by a flexible linker. It can be rigid as well. The PROTAC then brings this target protein, the E3 ligase, into close proximity for it to be polyubiquitinated and then degraded by the proteasome. So this provides an alternative strategy. Instead of just mere inhibition of a target protein, we can actually get rid of it entirely. So just this little schematic to explain further. So when you have the target protein and E3 ligase, they will not interact together. Well, when it's not the E3 ligase's natural substrate, they won't interact together. But when you add your PROTAC, a ternary complex is formed between your target protein and the E3 ligase. Polyubiquitination can then occur from the E2 conjugating enzyme. The PROTAC is then ejected and also leaves behind your tag target protein. And then this is recognized by the proteasome, and then the protein is degraded. So I mentioned that the PROTAC itself is ejected before the proteasome can degrade your protein, and this is true. And this site, you can think of PROTAC as a catalyst. Basically, it works in a catalytic manner. So it first forms this. It first forms a binary interaction between either the E3 ligase or the target protein, and this is in constant equilibrium. A ternary complex is then formed, as I said, between the E3 ligase and the target protein. Ubiquitination, and this can also be deubiquitination as well, so this is always in equilibrium. And then once the target protein is degraded, the PROTAC's ejected before the protein gets degraded. So a few years, 7 years ago now, our group published one of the first major PROTACs in the field, MZ1, which targets the Bromo Tag terminal domain proteins. And it does this by using this pan-selective inhibitor, which is Xavi in the previous talk briefly mentioned. So JQ1 here is a pan-selective inhibitor for the BET proteins. And when it's pan-selective, it means it can bind to these highly conserved bromodomains, which are found in all four BET proteins. So we take this ligand and we connect it to a E3 ligase ligand, which in this case is the von Hippel-Lindau E3 ligase. And this ligand was actually co-developed by our group and Craig Cruz's group in the States. So this is connected by a short peg linker. And what is interesting is you can see from this Western blot here and also this graphical representation that we can degrade completely all target proteins, or all BET proteins, instead of just merely inhibiting them. And what's also interesting is, despite using this pan-selective inhibitor, which can bind equally, has equal binding affinities to both bromodomains, more or less, we can see that at low concentrations, that we are getting selective degradation for one over the other. And this was really the first time that we started seeing selectivity induced from a PROTAC on, when using a pan-selective inhibitor. And the reason behind this selectivity, and the group a few years later really did the extensive biophysical analysis of the ternary complexes that MZ1 makes between VHL and the individual BET bromodomains. And what you can see from this alpha lyser here, when comparing the ternary complex populations of each bromodomain when bound to PROTAC and VHL, you can see that it has a preference for the second bromodomain of BRD4, and this shows like a huge cooperativity. And just to explain it for those of you who don't know what cooperativity is, cooperativity is the ratio between, because we're now into the realm of a three-body equilibrium between a PROTAC and two different proteins. You can get the ratio of the binary interaction between a PROTAC and your E3 ligase ligand, and also you can measure the KD, or the binding affinity, of the ternary complex formation. And here you just take the KD from the binary and divide it by the KD of the ternary, or vice versa. You can do it with the target protein. And this cooperativity value alpha, if it's greater than 1, it's said to be cooperative. When it's equal to 1, it's non-cooperative, and also when it's less than 1, it's negatively cooperative. Also, we were the first in our group. We were the first to publish the first structure, the ternary structure of PROTAC bound to its protein of interest, and also the E3 ligase. And you can see here nicely that MZ1 folds in such a way to allow these new protein-protein interactions. And this is really the driving force of the selectivity shown in the bio data. So a couple of years later, a really nice study in collaboration with Kristen Riching and the rest of the guys at Promega. They did a really nice live cell analysis of how MZ1 behaves by using this HiBit tag and nanoluciferase technology that Promega developed. You can see here in this live cell assay that MZ1 rapidly and potently degrades all the target proteins, and especially for BRD4 and BRD3, it's prolonged degradation over the course of a day, or even longer. So how this HiBit, just quickly, how this HiBit works is the HiBit tag, which is just a few, several amino acids, is knocked into the N-terminus of a target protein by CRISPR-Cas9. This is introduced into this is now endogenously expressed in the cell, and this then meets this large bit inside the cell, and once these are complementary of each other, and then you get luminescence. And then when you add the PROTAC, you can actually see once the target protein is being degraded, you now get a loss of signal, a loss of luminescence. What's also quite interesting with this technology, you can do a nanoBRET type assay where you can measure the interactions in cell of compounds with the respective protein of interest, or the E3 ligase, by having this high bit, large bit, luciferase, and this fluorescent tag on a ligand. And what's interesting in this setup, you can actually use this to measure the permeability of compounds in cell. So I'll show you here. This is from cell lysate, so obviously there's no cell membrane. Well, it's been mashed up, if you like. And this is comparing VH298, which is a potent VHL inhibitor, and also MZ1. You can see that in lysate they are very, very similar, and if not the same, responses and binding affinities towards VHL. But when we look at it in this live cell format, you can see that VH298 is still behaving as it would be in the lysate, but MZ1, as expected, as it's huge and there's loads of hydrogen bond acceptors and donors, is poorly permeable. Oh, well, it's showing a right shift and is a lot, binds a lot weaker. Well, it doesn't bind a lot weaker, there's less of the compound getting into the cell. And also here on the other way around, you can see for BRD4, and this is comparing JQ1, the BET inhibitor, and also this DBET1, which is a BET PROTAC, which has a cereblon E3 ligase ligand, and yeah, you can see that they're lacking in permeability of just plain inhibitors. So I just wanted to bring you back to this catalytic cycle, and although MZ1 is from this data, you know, it's not permeable. Well, it has very low permeability. It's still super potent, and you know, it degrading the target protein to low nanomolar DC50s and IC50s, and this is solely due to the ternary complex formation formed between you know, the protein and the E3 ligase. So in this the catalytic cycle, I wanted to include this, and this is sometimes forgotten about in the PROTAC field and is now quite a focused on topic. Is the PROTAC even getting into the cell efficiently? Well, the answer is yes, because obviously it works, it degrades the protein, but how can we measure that to basically, you know, optimize these PROTACs into being better degraders? So that's going to be the focus on for the rest of the talk. A couple of years ago, in collaboration with Tori Klein and Scott Lokey in the University of Santa Cruz in the States, we started to investigate the effects on PROTAC cell permeability on various VHL recruiting PROTACs, which all, you know, have this VH032 ligand in similarity. And this was really to compare the permeability and also the physicochemical properties of just the inhibitor alone, and also as a PROTAC, you know, molecule with everything intact. And they used this the PAMPA permeability to, you know, measure what its permeability was through this artificial membrane, and we found, sorry, that PROTACs can lose up to, you know, 8,000-fold permeability compared to their binding ligand. So you can see here, compound 1, JQ1, has quite high PAMPA permeability, and also this compound here, which has the VHL ligand. So, you know, you can see that these values 16 and 5.6. And when you compare it to, say, for example, AT2, which is the lowest permeable PROTAC in the series, you can see that it's really, when you combine them, basically, it just, the permeability falls apart. So, because PROTACs are obviously very flexible in nature, and they have numerous hydrogen bond acceptors and hydrogen bond donors, it's quite good to compare the role of like intermolecular hydrogen bonds and how these affect the cell permeability of VH032 PROTACs. So when you compare these compounds to compound 7, compound 15, and 8 and 16, you can see that they have a similar molecular weight, the same number of hydrogen bond donors, and same number of hydrogen bond acceptors, but we are getting this decrease in PAMPA permeability. And this is to note that obviously these two compounds here have their linker attached to this, like with this acetamide here, whereas these compounds have coming out of this penicillium derivative here. And what's to note as well, this you know, this LPE parameter, that these compounds have, the compounds from the acetamide have a higher LPE, and this indicates that the potential of masking of solvent-exposed hydrogen bond donors. And if we go back to the ternary structure of, say, MZ1, you can see through, like this, just an example of this. So this is this nitrogen here, this blue atom. This can form intermolecular hydrogen bonds to the PEG linker, the ethers of the PEG linker. And also this leucine group was found to assist in shielding of this acetamide nitrogen, this hydrogen bond donor. So from this work, also what was interesting is they wanted to investigate the switch of removing a hydrogen bond donor to a hydrogen bond acceptor by an amide-to-ester switch. So you can see here, instead of the amide here and here, it's been switched to an ester. And you can see that actually this makes a difference in the permeability of these compounds. So in this case, 3 and 4 is twofold more permeable, and between 5 and 6, it's 1.5 times more permeable. And this is quite interesting. This motivated us to think, oh, can we, instead of, and as I mentioned in the previous slide, we know from our studies that this ter-butyl group can shield and mask the hydrogen bond doning nature of the amide. So if we move it away to the other side of this protein of interest ligand mimic, if you like, can we see a larger increase of permeability? And that's what really motivated the next stage, the work that I'm about to show you. So we want to further investigate the amide-to-ester substitution, and we want to first vary the lipophilicity and what size groups affected permeability. We chose an alkyl linker in this case, just to remove any additional intermolecular hydrogen bonds that can be formed through PEG-based linkers. You can see here we are getting larger groups, this adamantyl, this diphenyl moiety here, and this is just increasing the lipophilicity. So as I said, yeah, we're increasing it. So with this calculated log P, we're increasing the lipophilicity as shown here, and also in the experimental log B values, you can see that they are, increasing in lipophilicity. And what's good to see is that most esters are more permeable than the amide counterparts. Which is good, and we're also getting to now an increased permeability to what I showed previously on the previous slide. We also wanted to see whether these bonds were actually stable, and obviously the caveat with an ester bond in drug discovery is that they're easily hydrolyzed. So in this case, for these scaffolds, you can see that all amides in this human plasma stability assay were basically untouched, and unsurprisingly, you could see that the esters behaved worse in this assay because they're being hydrolyzed. But I think what's important to note is these compounds, which are above 60%, remaining after the study, which I think was over 90 minutes, that once you start to increase the bulk around this the ester to the alpha position of it, you can start to see that they retain plasma stability. Moving on now, we wanted to investigate the effects on varying the linker length or the linker constituents. So we chose to use the PEG1, PEG2, PEG3, and also the same alkyl-based linker as before. And what's interesting is, again, all esters are more permeable than their amide counterparts. Alkyl linkers, they're more lipophilic. They're showing a higher permeability than the PEG-based linkers, which is unsurprising. And the longer PEG linkers have lower permeability, and that obviously they're more hydrogen bond acceptors and lower lipophilicity. This is nice to see. So now, how can we apply this? We want to apply this strategy, basically the toolbox of mimics that we came up with, and we want to apply these parameters to active BET degraders and see if we could improve their degradation profile and also their physicochemical properties. So we took MZ1, which we published in our group, and ARV-771, which is a similar, which is a BET degrader as well, but it just differs by the shorter, more lipophilic linker, and also an extra methyl group on the VHL ligand, which is actually shown to increase binding affinity for VHL. So we want to synthesize a library of 8 compounds in total, which would vary in amide-to-ester linkage to JQ1 here, and also PEG-based linkers, alkyl linkers, or like this shorter, more lipophilic linker present in ARV-771, and also whether there's a hydrogen or a methyl group. So the calculated log Ps of these compounds show that the esters are more hydrophobic, which is unsurprising. And obviously, when you go to like examples here where there's more alkylic nature to the linker, it's more hydrophobic. And the main goal was to, can we improve the permeability of MZ1? So we adopted the same PAMPA permeability assay to this set of 8 compounds, and what was great is that we did see an increase in permeability, and there was a nice positive correlation between the calculated log P and this permeability. And you can see here that MZ1 is actually the least permeable of this compound set. And the compounds like OAB2, which is this compound with shorter linker, is one of the best at permeability. Also, this anomaly, this OAB1, this is due to its too high lipophilicity, and this usually falls in the insoluble A log P regime of this assay, which is why you start to see this drop in permeability, and you start to get a negative relationship. And what was really interesting about this is that even both we used the human plasma stability assay as shown previously, and all compounds showed excellent plasma stability, whether it be an amide or an ester. And this is really nice to see, and it must be due to how rigid and bulky JQ1 is at just blocking the esterase activity at this position. So this is really encouraging. We next used we wanted to see if these compounds actually work biologically in cells. So we used a Western blot technique in HEC293 cells and blotted for BRD4, 3 and 2. And I'll just put this here. So this table shows basically the calculated DC50s, which is the concentration at which half the protein is degraded. And you can see here that all esters are behaving better than their amides in each case. You can see this by the more green nature. And yeah, as I said, and the best compounds in each of the series. So the most striking compounds were the OARV, the version of ARV-771, which has shown a huge increase in potency to now nearly picomolar DC50s and low nanomolar DC50s, and also AB2 and OAB2, which are compounds which share the same linker as ARV-771, but just have this the one less methyl group in the VHL. We next wanted to test these compounds for cytotoxic in BET sensitive cell lines. So we chose to use MV411, which is a leukemia suspension cell line, and then 22RV1, which is a prostate cancer cell line. And you can see when comparing to cis-MZ1, which basically behaves like a BET inhibitor because it's inactive at the VHL end of the molecule, that we see this huge left shift between degradation and inhibition, and they have a marked anti-proliferative effect. in both cell lines. You can see from this data that the ARV compounds are actually the best in both cell lines, and the OARV-771 and OAB2 show potent antiprolific effect over their in-my counterparts in MB411 cells, and you see here with the values, 18 and 4, and then you're getting a big increase in potency. And what's also nice to see is that our most permeable compound by PAMPA is OAB2, and this is also the most potent non-methylated VHL ligand compound. So this is nice that we're starting to see a correlation between permeability and efficacy. What's also a phenomenon that's widely seen in PROTACs, when you start to see it, when you use a high concentration of PROTAC, it starts to it starts to saturate the binding of your protein of interest and also the E3 ligase. So no more ternary complex can form, so no degradation can occur. And you can see this by high concentrations. You see this. This hook effect where you get less effectiveness. And it's interesting that all the compounds hook in the MB411 cells at high concentrations. And in 22LV1 cells, which is interesting, is only 3 compounds, MZ1 or MZ1, maybe 1 hook. And these compounds, interestingly, are ones which have a PAMPA permeability of greater than 0.2 times 10 to the minus 6. So this is sort of encouraging, because it's basically saying these compounds, they're more permeable than the others, so they're more efficient at getting into the cell, and that means that there's higher intracellular concentrations. So the binding sites on these proteins are more saturated, and we can also see that here in this Western blot at high concentrations, just an orthogonal assay, that you can see this hooking of ARV compounds, and also OAB1, which is the most lipophilic compound in the series. We next wanted to measure the biophysical. We wanted to biophysically analyze these compounds and see how they were behaving, and whether this increase in potency was towards ternary complex formation, or in fact it was down to permeability. And you can see from this FP assay that we chose first to use BRD4BD2 as the protein to measure the cooperativity. In this schematic here, what you're seeing is this is just a PROTAC titrated in. If you pre-incubate a PROTAC with target protein, you can either see a left shift or a right shift. This is the ternary binding of your pre-incubated PROTAC with target protein to VHL, which is displacing the probe, which binds to VHL. You can see that all these compounds are positively cooperative when compared to the binary interaction, and the ester PROTACs didn't show any better ternary complex formation, which is crucial in this, which is a keynote to take from this, that the esters were all worse at binding to BRD4BD2. So this is basically highlighting that the improvements in degradation must be due to permeability. So just to complete the set, we wanted to analyze the whole, the whole BET protein bromodomain series. So that's 48 combinations. So we executed a lot of FP analysis of these, and you can see that all PROTACs formed cooperative complexes with all bromodomains, and the second bromodomain is preferred over the first. Esters are are weaker at binding to VHL than their respective in-my counterparts, and they're also a lot weaker at ternary binding between VHL and the individual BET proteins. And you can see that in each subgroup that they follow the same sort of selectivity in between either amide or ester. In the sake of time, I might have to skip through this, but these few slides are basically just showing comparing the linker lengths and saying that the compounds with the same linker have the same BET selectivity profile. Here with AB2, OAB2, and the ARV compounds, they are less discriminatory of the BET proteins, and they are likely forming different complexes to the ones with the longer linkers like AMZ1. So just quickly summarize all the data I've shown. I know it's been a lot. So the ester analog of MZ1 is 1.5 times more potent, degrading BRD4, albeit however, it's threefold weaker at binary and ternary affinities to VHL, forms less cooperative ternary complexes, but it's also tenfold more times more permeable by PAMPA. Another example, the ester analog of ARV-771 is a lot more potent at degrading BRD4. It's weaker at binary and ternary binding to VHL with or without protein, forms less cooperative ternary complexes, and you can see that it's actually more permeable by PAMPA. So again, it's just showing the link between this increase in degradation and the increase in permeability. Again, fourfold more potent in this case, weaker, less cooperative complexes, and big difference in permeability. So we can say from this that the degradation shown here is being driven by permeability, and what interesting is that is the highest permeability of the entire series, out of the ordinary VH032 based on most permeability BRD4, the single ternary affinity and cooperativity for BRD4BD2. Just another example of this in a technology that's just come out of our group, Bromo Tag. We've got similar building blocks to MZ1 based compounds where we tagged target protein, in this case BRD2, which has been tagged with our Bromo Tag. So these compounds selectively bind to the tag on any target protein of choice. So the amide here, you can see that it's okay, but it's not as potent as we've seen. It's actually quite slow. But when you introduce the bond here, you can see that DC50s of the target protein, 19 times more potent, 3 times more rapid at degrading the protein, and also has an excellent plasma stability window. And this can also, going back to the hook effect, that there's higher intracellular concentrations of the ester, and this is backing up the fact that this compound is able to get in faster to the cell and start the turnover of target proteins. So just a few conclusions. The simple bioisosteric replacement of an amide-to-ester is to increase lipophilicity and permeability. And in the case of PROTACs, was able to increase cellular efficacy. Ester pressure plasma stability. So it's nice to be able to use these esters used in other medicinal chemistry. The increase in degradation potency as a result, and that's showing that increase in potency is increased permeability and not in improvements in biophysical, ternary complex formation. And PAMPA is proven a reliable predictor of PROTAC permeability. And just quickly, last but not least, to thank the people involved in this work. So big thanks to Tori Klein in Scott Oakey's group, who did all the PAMPA permeability and made the initial toolbox compounds of the mimic compounds, and Conor Cragen, who really championed the Western blotting analysis, and big thanks to the rest of Alessio's group. And I welcome any questions. Sorry if I've gone over on time. But yeah.